Welcome back to learning about thermodynamics. This is going to be lecture 9. This is page 1 of something. We're going to start out with an example problem here. So we got an example problem. We've been talking about boundary work. We've been talking about a little bit about the first law of thermodynamics for closed stationary systems. Here we've got a boundary work problem, right? So I'm going to write out, if you've not seen me do this before, I'm going to do what we normally do for good problem solving. I'm going to write out our givens, what we know. This is a piston cylinder containing steam, that is water. And again, once I've got all my givens recorded off the problem statement, I'm going to go back to a full-size camera view. So we've got water. And anytime they say steam, that's an indicator that I have water, just not in the liquid form. I have a mass of 0.3 kilograms. I have an initial pressure of 2 megapascals. I have an initial temperature of 800 degrees Celsius. We have a polytropic process. We're going to talk about what that means. Just a minute. We've mentioned that before in a previous lecture. We'll define what that means. They want us to find the boundary work. At a habit, I'm going to compute that in the out direction. So W sub B also sub out. So the boundary work out. This is an example problem. And they've given us a final state here. They've given us two properties of the final state, that is a pressure of 1.6 megapascals and a temperature of 500 degrees C. Okay. All right, I think that's all of our given information. So I'm going to stop share here and go to full screen here. All right, so these are the things we're looking for. Where these are the things we have, and this is what we're looking for. We're looking for the boundary work. So when I'm in the classroom, what I normally do is I'll wait and I'll look at my students and I'll say, okay, where do we start? Because we've done step 1 is what we're looking for. Step 2 is we've organized what we know. Step 3 for problem solving is, all right, what are some good tools or relationships or laws, equations that we can use that help us solve this problem? So, okay, well, what are we looking for? We're looking for boundary work. That is an energy term. So a good gag reflex, anytime I'm looking for an unknown energy term, might be the first law. But kind of like we had a previous problem where the problem with the first law here, you could write it out. We've talked previously about how do you write a first law equation. You're going to draw your system, and I'm going to draw a piston cylinder, and you're going to draw all the energies crossing the boundary. Well, there's nothing telling me I don't have heat transfer. So I'm probably going to have heat transfer occurring, and I'm going to have boundary work occurring. So there's going to be two unknowns in the first law equation. So I could write the first law, but I'm not going to know the heat, and I'm not going to know the work, and I'm only going to be able to solve for one of those. So I'm probably not going to be able to solve the first law for that. You're welcome to go down that path. But what I would tell you is when you're looking for boundary work, sometimes it makes just as much sense to look down the path of, well, do I have everything I need to know to use the definition of boundary work? Boundary work, by definition, if you compute it in the out direction, is the integral from the initial to the final volume of how the pressure varies or changes with respect to volume. Again, work is what happens when force is applied over distance, and the distance that it's being applied over is basically the change in the volume, the area times the distance. So what this tells me is I need to know a few things. One, I need to know these volumes to find my limits of my integration. Well, I know pressure and temperature at both states, so I could find the specific volume. With the mass, I have total volume. So I do know the volumes at both state 1 and 2, or at least I should be able to find them using property tables because it's water and I've got extensive water tables. I do need to know, though, for the calculus part, I need to know how pressure changes as a function of volume, and they've told me that. They've told me this thing is polytropic, meaning PV to a power n is equal to C, where n and C are constants. So I know that PV to the power n is equal to C, which is the same as saying that P is equal to C over V to the power n, which is also equal to CV to the minus n. However you want to write that, those are both mathematically the same. So I know pressure, I can plug in for pressure here, a function of volume, constant times V to a constant power. Now I need to know these constants. But what that tells me is I know this, I know these volumes. So long as I can find C and N, I can find the boundary work. Okay. How does that help us? Well, now we go further down the rabbit hole. This is typical for engineering courses, is you're going to have to be solving multiple step problems. Why? Well, because we're going to train you to be engineers to solve problems that we don't know exist yet, and to solve problems that don't exist yet, you're going to have to solve other problems that probably you don't even know exist yet either. That's just what engineers do. We just get used to it. Okay, well, what's not known now? Well, now I don't know C and N. Okay, what are some good tools or laws or relationships I can use to find C and N? Well, not a lot. In a polytropic situation, which is kind of a more realistic situation, I would need this piston cylinder of water in front of me, and I could actually test it at a couple places. And then once I've tested it, and once I know the volume at a couple of places or tested it somehow, then I can use a little bit of math to figure out what C and N are. What does that math look like? Well, here's what I know. This is the power of the polytropic expression, is we know that if I take P1 times V1 raised to this unknown n, that's going to equal a constant. And the same is going to be true at state 2. So C and N are unknowns, but notice I've got two equal signs here. I've got two equations with two unknowns. In theory, there should be enough algebra to find both N and C if I can find pressure and volume, which I need to find those anyway. How do I find those? Well, I've got property tables, but those property tables are not going to have total volume. What those property tables are going to have is they're going to have specific volume. So the way that works is it doesn't matter how big my system is, the specific volume is going to follow a trend based on pressure and temperature. So given pressure and temperature, I can find specific volume. And once I've got specific volume, then I can find total volume. And once I've got total volume, then I can find C and or N. Once I've got C and N, then I can perform my integral and I can find the boundary work, which the whole problem is asking for anyway. Clear path to a solution. If you're in my class and this is a 25-point test problem, you're getting really close to 15 points at this point, 60% of the credit, approaching a point where you basically have shown me, you know what, given enough time, you've got enough equations here, you can solve for your unknowns. Now, I do need to find these specific volumes. Let's start putting some numbers down here. So how do we find those specific volumes? Now that becomes the unknown. How do I find specific volumes? Well, I need to use, these are specific volumes or properties. I need to find unknown properties. For water in R134, I've got property tables, and the rules for those property tables is I need two properties at each state, at least two properties. Well, in this case, I've got pressure and temperature, which is normally enough to find those properties. So I need V1 based on P1 and T1. And I need, I'm just going to write it over here. Based on P2 and T2, I need V2. Now, again, I'm hoping you have learned how to use property tables at this point. If not, you really need to learn how to use property tables. That's previous lectures. You're welcome to go look at them. In fact, I would encourage you to. So at 2 megapascals, that's state 1, at 2 megapascals and a temperature of 800 degrees. So we take our straight edge. I would suggest a ruler or a sheet of paper or something that you can kind of isolate that row. There's my row for 800, lines up the pressure block of 200 megapascals or 2 megapascals. Notice this is the saturated temperature in parentheses. We are well beyond that. We're out at 800, so we're way beyond that 212. That puts us definitely in the superheated table. So that is 0.24674 according to the 6th edition of Changle and Bowles. I'm assigning homework out of the 10th edition. That's the current version. But I've got an old 6th edition PDF I can display here and not monetize, so I'm not making any money here, and this is educational purposes. I said that. I feel like I need to say that every time. State 2, I've got a pressure of 1.6 megapascals. Again, the temperature, the boiling temperature of water at this point is 201 degrees C. I'm down here at 500, so I'm well into the superheated vapor region at this point. Specific volume at state 2 is going to be 0.22029, and the units there are meters cubed per kilogram up here. Oh, I don't know why it's highlighting the whole thing, but anyway, up here are my units there. Okay. I think that's all I need out of my property tables. Okay. So with that, I can find my total volumes. Might do that in my head or even just writing it out, but let's just knock this out real quick. That means V1 is 0.3 times 0.24674. That is 0.074022. You could drop those last figures, but this is an intermediate number, so it's okay to carry them right now. That is going to be, I've taken kilograms times, again, I'm taking the mass, which is 0.3, multiplying by this specific volume. So 0.3 kilograms times this value. The units left are meters cubed. And then V2, that's going to be 0.3 times 0.22029. This is 0.066087, and those are going to be meters cubed. Okay. Now, what's next? What the heck am I looking for? Well, that's always a good question to ask. A good problem is one where you got to go back and say, what the heck am I looking for? I'm looking for the boundary work. What do I need to find boundary work? Well, I need to know pressure as a function of volume, which I have. And to find pressure as a function of volume, I need C and N. To find C and N, I needed P1, V1, P2, V2. Now that I know pressure and volume, N and C are the only two unknowns in this equation, or these two equations here. Okay. You can solve for, it looks like we're going to have to solve for for N first. Once I've got N, C is going to be pretty easy. Here's where I would pause and I would ask my class, okay, who can tell me what is the tool that I would use to try to find an unknown exponent? And what is that? Can you tell me what is that? I need to find an unknown N. How do I find an unknown exponent? And normally, begrudgingly, somebody will kind of mutter under their breath, logarithms. Yes, that are everybody's least favorite mathematical operation for some reason is the logarithm. This one's actually pretty straightforward to work with. Here's what I can do. I'm going to take P1 V1 to the power n, and I'm going to set that equal to P2 V2 to the power of n. What have I done? I've just taken these two expressions here, and I've substituted around C. So I set this equal to that. And then from there, I'm going to solve this out. I'm going to say that I'm going to put these ratios. I'm going to put pressures in a ratio. That's going to be P1 over P2 is going to equal V2 to the power n over V1 to the power n. And since both of these are raised to the power n, that means their ratio could also just be raised to the power n. The ratio of V2 to V1 to the power n. Okay. And with that in mind, then we can apply some logarithms here. So I can take the logarithm of, well, let's do this. If you're like me, that logarithm algebra maybe is a little bit rusty. So here's the thing. If we take the log of any base, I'm just going to use natural log, log base e, log of any base of x to the power y. Natural log of x to the power y. That is the same as y to the natural, I'm sorry, y times the natural log of x. Those are the same things, right? So since those two things, since that is true, what I can do is I can take the natural log of this ratio. That's going to equal the natural log of this ratio. So that means if I take the natural log of this ratio, P1 over P2, natural log of P1 over P2 is going to equal then the natural log of this V2 over V1, and that ratio is getting raised to the power n, which is going to be the same thing as I can now pull the n out of the parentheses, out of the argument, and put it in front of this natural log, just like I do right here. So I'm going to take this n out. Now this is n times the natural log of V2 over V1. Let's make sure I didn't mix these ratios up. Double check my algebra. It's a good thing to do here. This to this looks right. Yes, natural log this, natural log 1 over 2 is equal to natural log 2 over 1. Pull the n out. Yep, so far so good. So n then is going to equal the natural log. So if I solve for n, that's the natural log of P1 over P2 over the natural log V2 over V1. And in those of you that are really good at algebra and logarithmic algebra, you're probably yelling at your computer right now or your phone, whatever you're watching this on. Steve, you can simplify that. And yeah, you can, and I don't care. These are just numbers I'm going to plug in a calculator. So let's do that, shall we? We'll go ahead and write this out. Remember, P1 all the way back up here. When in doubt, go back and look. P1 is 2 megapascals. P2 is 1.6 megapascals. That's megapascals over megapascals, so I'm not going to write those, but I am going to write the 2 over 1.6. Since it's the same units, top and bottom of the ratio, those units are going to go away. Units are non-zero, so they can technically cancel out. And then I'm going to divide that by the natural log of V2 over V1, which we've got here and here. V2 is 0.066087, that is meters cubed, divided by V1, which is 0.074022. Again, I'm not going to write the units on this one. It's very rare that I don't. But there's enough going on there that we're okay. If you guys are okay at the units cancel out, I'm okay at the units cancel out. Okay. I'm going to do the bottom first. I'm going to take 0.066087. I'm going to divide it by 0.074022. I'm going to take the natural log of that. Now I'm going to invert that. I'm going to take the reciprocal of that to move that to the top so I can multiply by that. I've got a simple calculator, so you got to do some creative things. Now, so I'm going to multiply that number by, I'm going to put in parentheses, 2 divided by 1.6. I need to take the natural log of this quantity and multiply it by the value I've got stored in the calculator there. And I'm getting about a minus 1.9, we'll say 1.97. Okay. About 1.97. Now, here's the thing. What the heck is, okay, are we done? What the heck are we trying to do? Well, we go back up here. What the heck are we trying to do? We're trying to find boundary work. How do we find boundary work? Well, I need to know how pressure is a function of volume. To find pressure as a function of volume, I need to know C and N. I've just found N. minus 1.97. So I'm going to be integrating, right? I'm going to be integrating CV to the minus n with respect to v. Take this, plug this in there for p. Now, c is just going to be a constant. It's going to come out of the integral. Now I'm going to be integrating v to the minus n. Now, I'm perfectly capable of and don't mind integrating to the minus 1.97. If you guys are okay with the fact that this problem is already complicated enough, you're more than welcome to perform it for 1.97. I'm going to make this integral a lot simpler, and we're just going to say, you know what? Let's just call it a minus 2. It's going to make this integral integrating to the negative 2 or positive 2 is going to be a lot easier than integrating to the 1.97. It's not at all possible. It's just a power rule. I'm sorry, it's not at all impossible. It's just a power rule. But we're going to say n is approximately minus 2 just for a classroom example. If it was a homework problem and you've got plenty of time, then go ahead and do to the 1.97. But just to keep this a simple example, simple, as straightforward as we can for an example problem, we're just going to call that a minus 2. And normally everybody in class, when I ask this question, they're nodding yes. Yes, let's please make this a minus 2. That makes the units a lot easier to deal with. They're going to be hard enough as it is. Okay. Now what? Well, remember back here, I needed to find n and c. Well, I've got n. Now I need c. Okay. So now I've got c. Okay. So I can do this. I can say p1 v1 to the power n, which we've agreed is about minus 2. That's going to equal a constant value. I could also do it for state 2 if you like. I'm just going to do state 1. Okay. That is going to be 2 megapascals. That's P1 times V1, we said was 0.074022. That is meters cubed. That's going to get raised to n, which n is a minus 2. Okay. Okay, that's going to be 2. Well, let's do this one first. Let's do 0.074022, and I'm going to raise that to a negative 2. I'm going to multiply that by 2. I get 365. We'll say 365 equals 365. Now we got to keep track of our units. They're going to look ugly, but they're really not that bad. I've got megapascals here. Nothing touches that. And I've got meters cubed to the minus 2. So that means we're dividing by meters to the 6th. Or meters to the negative 6, however you want to do that. What is, and somebody will ask, Steve, what is meters to the 6? I don't know. I don't think in 6 dimensions. It doesn't really matter what it is. It's just units that we got to keep track of to make sure our units cancel out at the end. That's all we're doing. We're just keeping track of units. So constants often end up with whatever units are needed to make the problem make sense. Don't overthink it, okay? It's okay to ask. I'm just telling you, I don't think in 6 dimensions, so I can't tell you what meters to the 6 actually looks like. If you can, good for you, right? You got a higher IQ than I do, and I'm perfectly fine with that. Okay, so we got C, we've got N. What the heck are we trying to do? We are trying to find the boundary work, which means I need C and N. I have them now. I've got volumes. I got to do a little calculus. Once I do a little calculus, now I'm just down to algebra and units, really just units. Okay, so we're back here. Boundary work out is going to equal the integral from V1 to V2 of pressure with respect to volume, and we've agreed pressure is now CV to the minus n with respect to volume. So I'm going to plug in here. I have a value for C. I'm going to go ahead and rather than plugging that in, I'm going to pull that out of the integral. It'll be C. I will plug in my value for n though. So I'm going to have V1 to V2, V to the minus, and I'm going to plug in n, which is a minus 2 with respect to volume. So I'm actually integrating v squared. I'm integrating v to the minus minus 2. That's just v squared. So that's easy enough. Boundary work out is going to equal c over 3 v cubed from v1 to v2. And I've got values for all these. Okay. Boundary work out equals 365 megapascals per meters to the sixth. That's going to get divided by 3. That's my value for C. And then I'm going to multiply that by V2 cubed minus V1 cubed. So V2 is 0.066087. That's going to get cubed. I'm going to write my meters cubed outside here. That's going to get cubed. Minus from that, V1 is going to get cubed. So that is 0.074022. That's also going to get cubed. And then that is meters. Both of these are meters cubed, and they're getting cubed. So that is going to be meters to the ninth. Meters to the ninth. Okay. Run these out. Probably could have shortened this video by pausing it as I do calculations. Maybe I'll try to do that in the future. 0.066087. That's going to get cubed. Minus 0.074022. That's also going to get cubed. Okay. And then that's going to get multiplied by 365 and then divided by 3. So you get what appears to be a very small number. Boundary work out is going to equal 0. It's a minus, sorry about that, minus 0.0142. Yeah, we could say 3, but I wouldn't go past that. You ever get excited when you see a number and you start writing it out like, oh yeah, there's a negative sign in there. Yeah, as you can see, I do that all the time. Make sure you get that negative sign in there. All right, units left. I got megapascals per meters to the sixth times meters to the ninth. That means megapascals meters cubed. And we've done these units before. Recall that a Pascal meters cubed is a joule. Again, we've done that in previous videos. This video is already long enough. Approaching 30 minutes. I don't want to make it any longer. So Pascal meters cubed is a joule. This means this is megajoules. So we could just say that this is minus 123. That is 14.23 kilojoules. Kilojoules. Steve, that is really hard. Yeah, it is. I don't know what to tell you. Sometimes it is. That's 2 pages worth. I mean, yeah, it is. Sometimes it be like that. It's okay. Now, here's the thing. Not all polytropic problems are this intense because notice if I gave you n, right? If that was given in here, it says polytropic process with n to some power. Well, then I'm right here and I plug n into this equation. At most, I might have to solve for C. Well, I just need to know state 1 or state 2, solve for C once I've got n. I don't have to do logarithmic acrobatics down here to find an n. So polytropic problems, and this is kind of the worst case scenario for a polytropic problem. A polytropic process is if I know the n value, they're actually pretty straightforward. If you're allergic to the calculus, right? If you're allergic to the calculus, 1, I would get that allergy checked out. But 2, you can, there's a pre-derived formula that takes you from here to like a pre-derived solution. You can find it in most thermotexts. I don't mind you using that as long as you understand the rules associated with it. And it's normally just, it has to be a polytropic process where n is not 1 or something like that. Okay. So yeah, if you just can't do calculus, I really don't think this is the right place for you, but you're welcome to use the pre-derived formula there. Okay. All right. That's a good 30-minute video. That is plenty. If you have questions, leave them for me in the comments or send me an email and we'll pick up from there.